Okay, this is the introduction for the online rotational dynamics lab, and essentially we're going to be doing the same problem that we did last time, only we're going to be taking a look at this using torques and angular acceleration, and definitely not using energy. So you're going to go to the same setup that we had before. We're going to have a pulley, and we're going to have a hanging mass. Now we do not care so much about the height, and what we're going to do is we're going to use the same settings that we had before. We're going to decrease the inner radius to 0 millimeters. Lots of copy and paste here, by the way. And we're going to create a solid disk. We're going to calculate the theoretical moment of inertia, and you did that in your previous lab, so I'm not going to bore you with that. You're going to go ahead and click the start button and allow the mass to fall, and we're not going to record the height and velocity this time. We're going to use the velocity versus time graph to calculate the linear acceleration. So let's go ahead and take a look at this guy real quick. We're going to come back here, and I left this setup from last time. You click the start button, and this guy falls down. This guy right here is parabolic, and you would expect that because it's going to go like the t squared term. It is accelerating. And this guy right here looks nice and pretty and linear, and I don't know about you, but we can read off the delta t, and we can read off the delta v. There is a little bit of estimation going on here. And what we can do is we can say, aha, I know the most basic definition of velocity, or the most basic definition of acceleration is a change in velocity over time. So we can say that the acceleration is going to be the change in velocity over the change in time. What we can then do is we can calculate angular acceleration. I know the angular acceleration is going to be equal to the linear acceleration divided by the radius of the pulley. What we can then do is we can draw the free body diagram for the hanging mass, and what we should see is we should see some terms that look like tension, and we should see the weight of this thing. Heck, I'll go ahead and give you the free body, but it's up to you to go ahead and write Newton's second law for this guy. The free body for this guy right here, this guy is going to have the mass m. We're going to have the weight downwards. That's going to be the mass multiplied by gravity. This thing is accelerating down. Make sure that you call that guy negative. And we're going to have the tensional term right there impeding the fall of this mass. What you're going to do is you're going to write Newton's second law, and you're going to solve this guy for tension in the language of acceleration, little mass, and gravity. So there's my tension, there's my acceleration, mass, and gravity. Don't put numbers in just yet. You're going to put the numbers in just right here. Then what we're going to do is we're going to calculate the torque applied to this pulley. And I don't know about you, but there's a really good chance if I drew this pulley right here that I'm going to have this tensional term that's acting at this radius right there, and we can calculate the torque on the pulley. What we can then do is we can write Newton's second law for the pulley, now in the language of rotation, and solve for the rotational mass of this pulley. Much like before, you're going to compare the value that you got right there with the theoretical that you derived earlier, and there's a really, really, really good chance that the error is going to be relatively low, roughly 0%, and that is because, well, simulations are perfect. There's a little bit of rounding, and there's a little bit in the estimation of the change in time. You're going to repeat this for the hollow cylinder and find very similar results.